Alright, hell yeah. So a subscriber asked me to cover the torsion proof. And I've done it a couple times, but I think I'm going to start with this value of shear stress. Now, shear stress is in units of force divided by area. And I try to teach myself that if I see this term, that I just know it's, I'm just going to say it is force. Like if I have this means there is a force. This term just means that there's a force on an area. You know what I mean? So if I choose a little bit of area, I'm going to have a force on that area. And this is why we start with, just maybe pulling on this cylinder. If I just tension this shaft or cylinder, what we know is that the pressure that develops is going to be uniform, on a cross section. Given a slice, it's going to have the same pressure, and so we're going to have this letter tau for shear stress, which is units of force per area, and then we're just going to take the area. The whole area is going to be multiplied by that number to get the force. And in tension, I can do that same thing. If I know that I have a tau or a shear stress, I know that I have a force in that shaft, like axially, whether in compression or tension. And I know what that force is. I know the value of the force. Just because it's this number times the area. Okay, so a few things pop up when we talk about torquing or torsion, torquing a shaft and twisting it. One is that we're no longer pulling in tension or pushing in compression on something. We actually are shearing. And then so we have to understand that when we shear, we are sliding two pieces of material across each other, and it's the area in between those two pieces that is holding the strength. I think that's kind of a decent way to explain it. Yeah, because hell yeah. And I don't have my writing tools, so this is just, using words to explain that. Cool. Still, so this is representing that. Tau represents shear, and I apologize even, because if I have compression and tension, we don't use this Greek letter tau, which has units of force per area. We use another letter. It still has units of force per area, but we use sigma. Sigma is the Greek letter that signifies normal stress, stresses in the axial direction. Once we see tau, we know that we are dealing with material sliding past each other. So it's not getting crunched, it's not getting compressed or tensioned. Two pieces of material are sliding past each other. And this is where I would want to break out my drawing and writing skills, and just to show it's just like, well, it's kind of, shear is still like a leveraging of molecules, because if I drew those four molecules and like sheared, one side up, one side down, what happens is that you get two molecules to get farther apart and two molecules to get closer together. So even when you're shearing stuff, you're still tensioning and compressing. And it's because I'm just going to say this, it's because all materials are, bound together by electrostatic forces that must go through their mass, where you have positive protons and, and a sea of electrons, but still those interactions still have to go through, the mass of an atom. Hell yeah. And so cool. So we have this value, and we know that it, I'm going to say it's proportional to some sort of force. Now that force is the force needed to, what we say, shear, to take, to slide two pieces of material past one another. And that's where I also would bring in my drawing tools and say, if you're sliding two pieces of material past each other in shear, then you have an upward force and a downward force. But those two forces are separated by the distance, you know what I mean? Because if I just had those forces in line, you'd be compressing it. But shear is having one force up, one force down, and a distance between them. And if I had that, the thing's just going to spin. So that is the aha moment when you're just like, oh, okay, I get it. If I'm shearing something, I need also equal and opposite forces to counter those. And what we talk about, from our analysis is we take a little chunk of material, and it's best to make it a square. Because if I have an upward force here, or a downward force and an upward force, separated by a distance, on two faces, on the other faces, I have to balance those, and they're going to be the same magnitude of force. And that is like the aha moment also when it comes to shear. You're telling me if I shear a bolt and put a known upward and downward force to make that bolt shear, I'm also putting a sideways force on the top and a sideways force on the bottom that's equal to those forces? And the answer is yes. And then, break out the drawing tools and we can say like, whoa, it's just like what you think you're just putting force in, to shear something up and down, you're actually kind of doubling that. And so I'll just say kind of, because in a sense, that's where you get, like, it takes, half the effort, they say half the effort to, half the force to shear a bolt. Well, it's because if you're applying that upward force and downward force, you're applying the other forces, and some other things come into it. But I think that's a good enough explanation. All right, so hell yeah. So this shear stress is still associated with some sort of force on some sort of piece of material. The piece of material is going to, we want to know, and it's going to be proportional to the area of the piece of material. And I think this is a good time to talk about that axial stress again. If I have a bar that's being, tensioned, and then I draw a little... And a lot of the diagrams, they'll draw little squares. It is very useful to draw a three-dimensional cube. Because let's say I have this in tension, and I draw a little cube of material, somewhere in it. It's only the face on this face and that face that is getting tensioned. You know what I mean? Let's just make it simple. Let's say there is no, force on the other faces. Even though that's not quite true because of Poisson's effects. And hopefully I even said that right. There's some nuances where like the vocabulary. But anyway, so, but hell yeah. And then the face that you're actually putting the force on is the face that is, kind of facing the direction of pull. If I'm pulling this way on this cylinder, the face of this area, the perpendicular to this area is the direction this area is facing. So that force is in the same, it's parallel to this face. Where shear is the opposite. If I'm just taking this whole, if this is a bolt and I'm trying to reef it up, one end reef up and the other end reef down and trying to break it in the middle, then what's resisting those forces is, this, now am I even saying this right? Yeah, it's this cross-sectional, it's the cross-sectional face. But in this time, I have an upward force that is perpendicular to this face. This face is still facing that direction axially. But when I'm trying to shear it, I'm actually putting the force perpendicular to the direction that face is going. And then I'm trying to put a downward force over here. Cool. So whatever force that I'm applying up and down, and then whatever that face, the area of that face is going to dictate what this stress is. The stress is in units of force per the area that's getting sheared. Now when it comes to twisting something, this is where I do a visualization. You can visualize a solid shaft or cylinder, or I can visualize a hollow cylinder. I'm going to envision a hollow cylinder, and I'm going to envision that it has only one molecule of steel atoms thick. And then so there's just a ring of steel atoms here, and then next to it there's another ring of steel atoms. Now this is also, similar to when we pull on something axially. If I have a square bar and I'm pulling tension on one side and the other, I can take a slice of that bar, and what I get, or even just take a cross-sectional cut, if I'm putting a force on this end, on that cross-section there's that same force. And I can take any cut along that whole bar, and I'm going to get a force on that cross-section. That means that the molecules on that cross-section, or between two cross-sections, have to be attracted, to hold themselves together. So that might be one way to look at it. Same thing happens when we have, now back to our cylinder. That's one molecule in thickness, it's hollow. When we twist on it, and apply a torque, I'm essentially taking this ring of molecules and trying to twist it in a circle. And then I'm just going to envision the other disk of molecules is actually just welded to the wall. And for this analogy, we could have a bar, a circular bar that's just two molecules in thickness. At some point we're going to have to take a differential slice of this thing anyway, so why not just make our cylinder, the shaft the bar that we're torsioning, let's just make it two molecules, two disks of molecules in thickness, this direction. One is fixed and welded in space to maybe like a wall or a building, and the other is being twisted. And we twist something by applying, maybe a force up here and a force down there. So we apply a moment or a torque, and that has to be balanced. And so where we see that those forces are balanced, and we could even go one step farther and be like, well, let's make this as easy as mentally and visually as possible we can. So I'm going to say that I'm going to apply, instead of just applying just a big old torque, like welding another bar here and putting an upward force and a downward force that creates a couple or a moment that gets driven into this steel bar. Because even in that case, because the same things are going to happen with this steel bar as when we have just a rod that gets tensioned or compressioned. If I have a rod that's in compression, maybe here and compression there, and apply a load, am I applying the load evenly on that top surface? I don't know, maybe not. If I am applying a concentrated load, maybe. It takes some molecules to actually distribute that load where every slice then has that, And the same thing could be the case for, just welding on a little bar here and then tweaking it or torquing it. You might have to go into the rod, at least the diameter, to have that to be uniform. And then so visually, if I'm still going back to this as a hollow cylinder that's one molecule in thickness, what I'm going to do is I'm just going to put a force on every molecule, and I'm going to put that force in perpendicular to the direction of this circle, or tangent to it, and then each of those forces are going to take this disk of molecules and they're going to torque it. Those forces are a distance of the radius away, so each of them add up to be a total moment on this cross-section, and if we have that, this other cross-section over here has to resist it. And so that's what we have. And since we have two disks of molecules, I can take a cross-sectional cut between those. And so what this says is that if this disk is getting torqued this way, that other disk is like gripping this disk and saying, no, you don't. You know what I mean? This disk just wants to spin in space like a dynamics problem, but it doesn't. How does it not do that? These molecules over here are sprung or electrically attracted to these molecules, and they want to hold that back. Now again, it can be easy to see that if I have two molecules right here, these are holding maybe compression, and if this one goes that way just a little bit, the distance did not change. But that's where you want to envision four molecules, one right there, and one right there. And then when these two molecules go up a little bit, hey, the diagonals do get farther apart, and then these diagonals get closer together. So that is the fundamentals of what shear does. If I just say these two molecules, you know what I mean? These two don't get very far apart at all. So those distances almost don't change at all. And so there is no extra force between those molecules or these two. But these diagonals, hell yeah, they're in tension and these are in compression. And now that doesn't, and those two don't make it so things shear twice as easy. What makes things, because we still have 4 molecules, I'm putting a force doing that, a shear force up and a shear force down, and I got 4 molecules in the system. 2 are tweaking up, 2 are tweaking down. Why? And I have twice the area. You know what I mean? Oh, no. I don't want to get into that. But anyway, I'll say wrong things. So we want to, the whole idea is just make this simple as possible. So anyway, so it's these molecules in this disk that are resisting these molecules. And cool. And we made our problem real simple, that we have a ring of molecules on this outer, that's what the cylinder is made of, a ring of molecules. And so if we have a ring of molecules all the way around, connected to another, you know what I mean, and we shear up on these, put little forces, well, we're going to have little resisted forces on all those other molecules. And those are the shear forces. And if we have a shear force, if we know the area or the amount of material that shear force is acting on, you know what I mean, the area specifically, then we know this number for shear stress. So to generate a moment, that part's easy. I just know this radius, and I'm just going to, you know what I mean, if I want a torque of 100 pounds, you know what I mean, or 100 Newton meters, all right, let's do 100 pounds. I want a torque of 100 pounds, and I want a stress of 100 pounds per inch. Sorry. I want a torque of 100 pound. Yeah, torque is in pounds times distance. So I want to torque this thing with 100 pound inches. I'm going to say this radius is 1 inch. So we have a 2-inch cylinder that's hollow. That's 1 molecule thickness. I want to put a torque on it of 100 pound inches. Since the molecules are 1 inch away, then I have to put a total force on these molecules of 100. So let's say there's 100 molecules in this ring. I need to put, every molecule has to take 1 pound of force. And it has to take it tangentially, because that's the distance, that's the torque that I want to apply to this cylinder. And if all those forces are tangential in this direction, I'm applying, or the opposite direction, I think that's what the picture shows, then we have this cylinder getting torqued in this direction. Hell yeah. And it's creating a torque of 100 pound inches. So now these molecules have 100 pounds and there's 100 of them. I'm going to take, 4 of them. And cool, I'm going to have 2 pounds down and then 2 pounds up. The area is on 2 molecules. So even though I have 2 molecules and each have 2 pounds, cool, if I have 4 of those molecules, the area is the area between 2 of them. So I have an area of 2. I have a force down on those 2 of 2 pounds and an area of 2. So this value for stress, for shear stress, is the shear force, which we said was 2 pounds down, and the area, which was 2 molecules, 2 area of molecules. We're just going to call those units of 1. So cool. And then so I have a shear stress of 1. Hell yeah. And I'm going to have that shear stress all over that outside ring. Okay, sweet. And now we're just we're on our way, for some equations, because what I wanted to, and even that did it though, that related the tension. That's all the whole derivation, to make it as simple as possible, is like, hey, I want to input a torque, which we said was 100 pound inches, and then I want to know what this shear stress is, and or vice versa. If I know that I have a limit on this shear stress, I want to know how much torque I can apply. So let's just do that. Let's just say I can only have these molecules be in a state of shear stress. which is a force per their area of 1. Cool. And I know that shear is molecules sliding past another, pair of molecules. Molecules sliding past molecules. So I'm going to have 100 molecules in this circle next to another 100 molecules, in another ring, and it's a hollow sphere. And if the shear stress is 1, that means, in reverse, that means that, so if you're given this number for shear stress, just know that it has units of force per area. And it's one of those physics quantities. Any physics quantity that has a ratio for its units, always take that number and divide it by 1, because that gives you the ratio. So if the max shear stress is 1, I'm going to take 1 divided by 1 and then say the units. That's going to be 1 pound, and we're in pounds, divided by 1 unit of area. And we're just going to say 2 molecules is 1 unit of area. Each molecule can take 1 pound. That's just the universe we live in. We're not talking, even though it's moles of molecules, and each molecule can take a significant negative exponential number that's difficult to even quantify. We're just going to say, hell yeah, every molecule can take 1 pound, and its area is 1 unit. Cool. So that's our value on shear. 1 pound divided by 1 unit of area of a molecule. Now, every molecule on that outer ring sees that. Cool. And then just a little foreshadow, why is this triangular? Well, nothing happens in the center of a torsioned bar because it can't take any torque. The whole idea of this is that we have these molecules at this distance of r, let's say, in this ring of this hollow sphere. That's the easiest one to visualize. And we can put a force that's tangential, and it's going to be all in the same direction. You know what I mean? So, cool. So let's use this number. And again, the whole idea was if we see this tau or shear stress, I know that this is just telling me what the force is. But you know what I mean? I have to do my due diligence and figure out what the area is. But I know the area. I have 100 of them. I have 100 molecules going around this cylinder, and therefore I'm going to have 100 pounds. So it's just that simple. Cool. It's going to get more complex when we say, well, this ring of this cylinder is actually made of 100 here, and then 90, and then 80, and then 70, and then 60, and it's made of ring after ring. And then each of those can only take the pounds. If I have a ring of 80 molecules, cool. They can get maxed out at 80. But we're going to see though, if those got maxed out at 80, then the ring above it would be higher than the max. So that we can talk about that right now. If I have a ring of molecules that's getting maxed out, it sees a stress of 1. The inner rings, see less, and it's linear. The ring right at the center sees no stress. A ring halfway at a radius of r divided by 2 will see a stress of 0.5. If I'm saying this outer ring sees a stress of 1, which is 1 pound per unit molecular area, at the halfway point, those molecules will have a stress on them of 0.5 or 1/2 pounds per molecular area. And you're going to have less of them. So not only... And we can actually do this, like a circle is fairly linear, or it is totally linear. If this is the circumference and there's 100 molecules on this outer circumference, if the radius gets reduced by half, it's the same thing as if the diameter got reduced by half. And therefore the circumference gets reduced by half. Some of these you never know if it's like a square root relation or a square relationship. But when we're just talking circumference related to diameter, or circumference of 100 related to a radius, if the radius gets halved, we're going to have 50. So now in the center, we're going to have 50 molecules that can take 1 pound each, tangentially, but they're only a distance of half the radius. So therefore, which is half of an inch in our case, because we're having a cylinder of a radius of 1. So we have 50 molecules times a half times a half. That's 50 times a quarter. You know what I mean? That's 12.5. So this can only provide 12.5 pounds of torque. So if I had 2 rings of molecules, one ring that was 100 molecules, that's maxed out, and then another ring that's rigidly attached, you know what I mean, because that's what our cylinder is made of, then if I max out, if I know my stress is 1 on the outer surface, that can provide a torque of 100 pound-inches. The ring in the middle can only provide a torque of 12.5. And it just gets worse after there. If I went in another quarter, you know what I mean, I would have not 50, I would have 25 molecules. So that's 25 pounds. They would be at a distance of a quarter. And how does that work? Oh, yeah. No, it wouldn't be 25 pounds either. It would be, I would have 25 molecules that aren't seeing aren't seeing a stress of 1 pound per molecule. They're not seeing a stress of a pound per molecule. They're seeing a stress of a quarter pound per molecule. So not only do I have 25, of those 25, they're only seeing a quarter of a pound each. And they're only a quarter of a distance. So I have 25 divided by 16. I'm just going to say that's about, I'll even give it a little bit more. I'll just say it's 2 pounds. So this ring at halfway, was tensioning, can have a tension of 12.5. The outer ring can have a tension of 100. And the ring at 3/4 can have a tension of 2. So we have 2, 12.5, and 100. And let's just simplify it. Let's say we have 2, 13, and 100. So now we're up to 115. That's it. So our torque on our bars is 115. Given that we know the stress on the surface. And so for a lot of these problems, we're either going to have a limit of the stress, where we're just like, hey, the stress can only be 1 pound per molecule. That was our problem. Let's say these molecules can take up to 5 pounds per molecule. You know what I mean? So we're not at the limit. We have a factor of safety of 5. We just want to know how much tension we can actually put on this cylinder. And our cylinder is made of one ring of molecules at the radius, another ring of molecules at the halfway point, and then another ring of molecules at the 3/4 point. And the answer to that question, if my stress can only be 1, even though this system can take up to 5, we want that factor of safety, then we get this 100 inches squared. 100 pounds per inch for the torque for that outer ring, 12 for the halfway point, and then 13 for that halfway point, and then 2 for that 3/4. And so we get a total torque of 115. But you can see how it gets diminished. So even though this just seems linear, where we have a value out here, and then we have a value of a half, and then we have a value of 3/4. Well, yeah, that's where this term, sometimes it gets a little heady, because this is the units on it are force per area. Or you could think of force per the molecules that you're dealing with. So it's also a force per volume. And so what is the area or the little volume or the number of molecules we're talking with? Well, we said that if I was on the circumference, I have 100. If I go halfway, I get 50. If I go another halfway or from there, I get, just a quarter of 100. So I get 25. Cool. And we think that's fairly linear. But then we realize that this value is just a force, per molecule. So then we have to say, and I'm doing that wrong. Anyway, I should just be saying, hey, because the equation that they use is like, if I have a value of 1 on the outside, which is 1 pound per molecule, I have a value of 0 in the middle, then the molecules at the halfway point are seeing 0.5. And that's the value of the shear stress, 0.5 pounds per area, per unit molecule. And then at this quarter is going to be 1/4 pounds per the molecules that we're dealing with. And I've been talking about unit molecules, where it's just the area of, a ring. But, like, what are you going to say? You'd have to actually divvy this cylinder up into, what we've been doing is, I don't know. You would have to divvy it up into rings and then say, hey, if I have a ring of area, like let's just do this ring right here, and then just that outer portion. Cool, that's the material, but you can see some of that material is at the full radius, and the other is just slightly over here. So we're doing a poor approximation if I'm saying all the area is at the outer radius, all the area is in the center, all the area is over there, and even just averaging it in the middle, you can't get a perfect value, because we're not only taking, because we did three things. One is that we have this stress on the outside of 1 pound per molecule. And then once we know how much poundage we can put on each molecule, we have to count the molecules up. And so we have this number of 1 on the outer surface, a number of half, and a number of 1/4. But on the outer surface, we have 100 molecules. And so 1 times 100 is 100. And that's only the second step. We have a third step after that. But let's go to the halfway point. We have a value of 0.5 pounds per molecule, and we only have 50 molecules. So that's a value of 25 pounds. Cool. And we're still not done with that third step. You go to 3/4, we have 1/4 of a pound per molecule, and we have 25 molecules. You know what I mean? So we have, is that like 12.5? So we have 25 times 1/4. So half of 25 is 12.5. Half of that is 6.25. So we have 6.25 pounds, of force. But, we have to do that third step of saying just finding the force isn't good enough. We have to say those forces are a distance away from the center and are balancing the overall torque. So that 6.25 pounds is at a distance of 1/4 of an inch. So not only do we have 6.25 divided by 4. That's where we kind of get that value. Let's just say 6.25 divided by 3. That's that value of 2. I'm being generous. This value here we said was, I have to go back. That's the whole point. It's like the juggling part of it. The stress on the perimeter is 1. The stress at halfway is half a pound per molecule. We have 50 molecules. That's going to be 25 pounds. That force is a distance of a half an inch away, and so I have 25 pounds times half inch. That's going to be 12.5 pound-inches of torque. And sorry I didn't put the units on the first one. That's going to be 6.25 divided by 4, or we're just saying is 2 pound-inches of torque. On the outer surface, we have that stress of 1 pound per molecule. We have 100 molecules. That's going to be 100 pounds, and it's a distance at 1 inch. So that gives us 100 pound-inches. Hell yeah. Cool. And we can do it in reverse. You know what I mean? I can say I want to apply a torque of 100 pound-inches. I got a device that can measure that. Now I want to know what stress is happening on the outer surface, which is the surface that sees the max stress. Because, I don't know, maybe this material can only take like 0.8 pounds per inch per molecule. 0.8 pounds per molecule. And if I put less torque at 100, what's the value of this? Well, then you got to do that process in reverse. You have to say if I have 100 pounds of torque, and then you'd have to almost do an iterative or guess and check process. So now we're going to get into the calculus. And it's just fascinating. What bummed me out about this derivation is they did, that's why I'm starting with this idea of shear stress. because I get kind of winded. I'm going to drink some water right now. Yeah, I kind of get winded where it's just like the farther you get into a textbook, that's why the last chapters of the textbook, you're just exhausted and you're just like, these are the hardest, sections to learn. You should almost learn them first, when you're totally fresh. That's kind of what we're doing. We're going to this idea of shear because we just have to use this equation and we're going to, disregard this inside because this inside portion is something to do with the fact that when we twist something, it actually twists. And I'm just going to make it easy. Like if we have these two rings of molecules and then I twist on them, molecules can't, shear very far. If it's steel, the angle that appears is super tiny. It's 0.004 radians. And so as this length of this shaft is really small, this hardly rotates. But each ring of the shaft can and does rotate maybe that max 0.004. That's going to be maxed out. And so if you have a long shaft, even 1,000 millimeters, even if it's just a meter long shaft, because of the small angle approximation, and you can, you don't have to use small angle. You could actually just but you have this angle of 0.004. And you have a length of the shaft of 1,000. Which small angle just says, hey, that's going to be equal to the hypotenuse, the length of the shaft, and when it rotates, the hypotenuse is going to be the same length anyway. So you have a hypotenuse of 1,000 and an angle of 0.004. So that distance, the arc length that it actually rotates, is 4 millimeters. So cool. So that gives us an idea that if our circumference is 4 millimeters, you can just imagine something that's, like a thin piece of wire metal and 4 millimeters in diameter is still, 4 millimeters in circumference is, it's pretty thin, but I mean, it's 1 mil wire. 1 millimeter of wire is way thicker. Well, don't quote me on that. It is probably thicker than welding wire, 1 millimeter. I don't know if it's thicker or thinner. I'd have to do the calculation. Anyway, but that wire at a meter can rotate one full time and then, and then rotate back and be all in the same place. I will say that at least once is that material mechanics comes down to like stretching something, or in this case, shearing something with angles. And as long as you're in that linear range, where shear has a value that's going to be like tau proportional limit, tau yield. That's the tau value, that's the shear stress, that's the number that you can get to, and then back off all forces, and your whole project, your whole bridge or whatever is just in the same location. Every molecule is in the same location. What got me on this proof was that this tau max is just saying that on the surface, that's going to be where you're going to find the largest value of shear stress, and then you have this linear relationship to the center. That's it. It doesn't mean, I just know that materials have a proportional limit and a yield limit, So I thought that was what they were saying for tau max, because I think it is useful to, when you're doing these proofs, is just like, hey, let's torque this thing where this outer surface gets to be that number of that yield where people might die. I think it gives you a little bit more paying attention room. And so that's what I envision for this tau max. I also, just envision its tau yield, and then, but that's not what they're saying, because a lot of the problems are just, we're going to have a factor of safety of 5. This value is just 1 pound per molecule. This material can take 5 pounds per molecule in shear. And so, it just means that if this is 1, this is half, and this is 0. So we're just saying this value is just the largest because it's on the outer surface. The reason why you have arrows going 2 different directions is because shear has to have those 4 forces. We said that if I have a little chunk of material, I pull down and push up, it would just spin in this direction. So I need to push that way and push that way. But if you are pushing the material that way and that way, then the surface above and below, are shearing past each other. And so those two surfaces can rip apart. So they're experiencing the same thing. And then so you have, if you're shearing a cylinder, and that's also, I think this is really good. When you're thinking of materials, also think of a material that you could put in some force. It's all rigid, it's hardly going to move, but then it's all of a sudden going to crack, And so with this, if this was made up of, what you would have with this is that you would crack on rings on the outer surface, or the outer surface is going to crack because it's going to see the largest force. And then this inner surface, these two surfaces are going to slide past each other. And so you can get longitudinal cracks. On this surface, you would get cracks in this up and down direction. And that's even interesting to think about, just because they show you one diagram of a piece of chalk where this is kind of what happens. We talked about just briefly that if you're shearing molecules, like it's kind of a clumsy way to rip two molecules apart. If I got four molecules, two go down, two go up, it's the fact that two of those molecules get farther apart. That's what this shows. So if this square is, like in this orientation, not shown, I'm going to have four molecules. I'm going to pull these two down, those two up. What happens is that these two get farther apart. That's what these two areas represent. And the other two molecules get close together. But what happens if this is a thing of chalk can take compression all day long. You know what I mean? Can take plenty of compression, ain't going to bust in compression, ain't going to crack in compression. But it can hardly take anything in tension. So what happens is that you get it to split right along this line. And every molecule, the second you get that to split, you get a chain reaction that the next molecule unzippers, and it splits right on that line all the way around. And that's the line that's getting the most, and it's 45 degrees. You know what I mean? Because that's what's that element. Because if this is our thing that we're torquing, if I draw a square that's in line with the element, this goes down, that goes up. It's those two molecules that are getting, it's the diagonals that are getting separated. These are getting crunched. The distances those molecules travel is so short. Molecules can only go, shear for rigid materials, those molecules don't travel very far. The angle is really small, 0.004, and the distance between molecules is incredibly small. So that remains a 45-degree angle. Even though you get a distorted shape, you get a break on that 45. Hell yeah, and that's where you get this 45 propagating all the way around a piece of chalk. Okay, sweet. So, So I think we're doing good, because at no point have I mentioned that this thing, because I'm still welding this shaft or cylinder to a wall. I'm saying this cylinder is just two molecules in thickness, and this can represent our whole, and we're applying a torque to the cylinder, and it's the internal connections. That internal slice has to resist that torque. So we've done a pretty good job. At no point have I said anything about the angle, of twist. I did mention that once, that between these two molecules, you get 0.004. And if I stack another ring after another ring after another ring, and this thing is 1,000 millimeters, 0.004 times the radius. So radians times radius is arc length, and we get 4 millimeters of rotation. If this circumference is 2 inches for our problem, our diameter is 2 inches, our circumference is 6 inches, that's about 150 millimeters. So let's say the circumference is 150 millimeters. If it's steel, the max rotation I can see is 4 millimeters. So there you go. So if I have 150, half is 75, a quarter is 30, let's just say 30, and I can see, or 35, and let's say I can see 5 millimeters, and that's 1/7 of 90 degrees. Let's say it was 1/9 of 90. I'm going to have 10 degree of rotation. I'm going to have less. I'm going to have about 8 degrees of rotation. So even with a 2-inch chunk of steel, that's 1 meter long, I can actually torque it. So visually, I can get it to rotate 10 degrees. And that's substantial. I can see that. And so that is kind of where this, the angle comes in. But it's not necessary. Because when it comes to, because we've already done the calculation. We already said that, hey, I either know the stress, and we're kind of there, we're kind of getting to that integration part. But all you have to know is like, hey, I know the value of stress, or we did the aspect of like, hey, I'm just going to say I know the value of stress. It's going to be 1. And we're going to go through that process to find the torque that's causing that stress. And then we could do the other way. We could say, well, if I have a known stress, what's the torque? But we see how you have to like add slices. You have to figure out what this value is on a slice. Cool. And then figure out how much area is in that slice, like number of molecules. Cool. And then multiply it by the distance that slice is away from the center. So that is the integration process. But I think it gets confusing when they first tell you all about the changes in angle and they introduce this twist rate, because that doesn't even come up for this integration. So the only equation that we need, if this is our tau max, and again, this is just the max value on the surface, what I want is just an equation for tau. And what's varying is the radius. So I'm going to say as I move from here to here, my value for tau, so at here, my value is tau max. So if I throw in a radius of r divided by 2, I should get tau max divided by 2. If I throw in a radius of r, I should get tau max. And then so we have to, and what's this value of r? If I'm saying r is just the radius, I can't use that as my variable. So that's where we introduce the term rho. And so I'm going to say rho is just any point along this radius. It would be like saying if x is the distance along here, then this point is L. So this would be the, if I have a shaft, this is my starting point, this is L, but this is any point along x. When x is equal to L, I'm at the end. So that's what we do for rho and radius. So hell yeah. And I think it's useful just to be able to, this is how I do it. I say, hey, if my equation, if I have to say rho is r, then I have to have r upstairs, and then I have to get out T max. So if I say r is upstairs and I have to have this T max, then I have to divide by r. So see, it's kind of that easy. And then if I throw in rho is equal to 0, 0 divided by r is 0, times T max is just 0. So you got 0. Let's try rho is r divided by 2. So I have r divided by 2 divided by r. That's going to be 1/2 T max. Okay, so this equation, and that's where it's just like, cool, sure, it is equal to something with the twist rate and all that. But I think that gets even just a little confusing. And so, hell yeah, so we're starting the proof from just knowing that this is a value. Shear stress is a value, and we need an equation as it varies along the radius. And that's it. This equation just has rho, r, and T max. T max is going to be a known quantity, and in the end, once we get our equation, we're going to have two quantities. We're going to have T max is equal to the torque. You know what I mean? So if I know the torque, I'm going to know T max. If I know T max, I'm going to know the torque. So I should say, once we do the integration, we're going to have kind of two variables that we're going to equate T max to torque. And we do that by taking a small little chunk of area and then knowing that that area is a distance rho to that little chunk of area, that differential area. Because I know its distance rho, I know what its shear is. And I know, if I know it's shear, yes, if I know what the distance to that area is, then I know what its shear is. So if I just want to know the shear at this little area, I want to, well, I'm going to say it's a distance rho. And then so I know what that shear is. Shear is this distance rho, T max divided by R. And so that's going to be the shear on that differential area. I know what the differential area is, and I just want to, and that's going to be the force. So that's the first thing. Shear times area is force. So I know the force on that little chunk. Cool. If I know the force on that chunk, I'm going to multiply it by the distance from the center, which is another rho. And that's going to be the torque generated by that little chunk. And then you can integrate radially and circumference, like in 2 pi radians around the circle to get the torque. So hell yeah, let's walk our way through that. So there you go. So this is the integration part. It says that you have tau, and again, tau from memory is just rho divided by r times T max. If rho is r divided by r is 1, and you get T max. If rho is 0, you get 0. So it's always just good to double check that and do the middle. If rho is r divided by 2, r divided by 2, you know what I mean? If we have r divided by 2 divided by r, that's 1/2 T max. So that would be what rho is. Hell yeah. Now, if I want to, the first thing you need to do is find the force. Like, know that shear is a force, but only due to the little area it's acting on. And what we've shown is that this area is going to be different than that area. It's going to be different than this area. Because it's, once we integrate, look at this ring. That ring is smaller than this ring. Cool, that's part of the integration part. Okay, so tau is shear stress, which is in units of force per area. That's pounds per inch squared. I want to multiply by the area, and that's going to give me force. So this is a stress diagram, a differential stress diagram. I could turn this into a force diagram, drawing the same picture, drawing that little dA of area, and then putting a force arrow. And that force arrow is going to be tau times dA. That's it. It's just tau times dA. So that's the first thing that we have, is that we have the force is tau times dA. That would be a force diagram. And then what we have to, understand is that force is a distance away from the center, and that's providing a torque. And why is it providing a torque? Is because we welded this ring to the wall, and then we're torquing this ring downward, and the system is balanced from statics. So there must be an equal and opposite torque the other direction, and that's being provided by the internal reactions. And so this is, so if I drew a slice right here, and I said this slice is torquing down, well, yeah, and because it's equal and opposite, I always hate, it's just like, well, how would I draw it? I think I would draw this slice getting torqued down, and that means that, if I did a free body diagram, if I took this slice and put it aside, this side of the slice would get torqued down, the other side would get torqued up. But I guess what they're doing is they're slicing this. So we got 2 rings of molecules. You're slicing this side off and putting it aside, and then looking at the internal guts of that new slice. And that new slice is also getting pulled down. At the wall, it's resisting that. So hell yeah. So this is that internal slice. And cool. And your force is this value times that little area dA. But the moment generated by that force is the distance rho. So that's the first thing we have. We have the moment generated by this force on this little area is tau times dA. That's the first 2 things I would multiply, because you have force divided by area times area. Now you just have force. You're going to multiply it by rho, and that's going to give you a a torque. That's going to give you your moment. And in this case, they're going to call it moment. And so let's see if they even do it in that order. And they don't. It's crazy. Look at this. They put that tau here, and then instantly they put rho. So dumb. They should put tau times dA, because tau is in units of force divided by area. Why not just instantly multiply by area, and then that becomes a force? And then you can multiply by rho, and then you can see that does a distance. Even torque sometimes gets written as F times D from a scalar perspective, and that's what this should represent. It should be tau dA times rho, even though it makes no difference what order you put these in, because they are, is it associative? Yeah, when they're grouped together, it doesn't matter what grouping. It doesn't matter if you multiply those two terms first, or rho times dA first, or rearrange terms and do it tau dA, which I think you should do first, just visually. And that's what sucks about some of these proofs, is just like they just don't put the letters in the most logical location, and so they don't spell that out for you. I don't know. So that's where it's just like I really like to spell that out for other people. Cool. So tau and dA is the force, rho is the distance, and that generates a little bit of moment. But that's just a small little chunk of moment. Every little square on this thing is going to, add up. So that's where we have this idea of adding, summing, and integrating. So it can be that simple, but I just know with and I wouldn't do it this way either, because in one more step they're going to give you an answer and it's going to suck, and you just lose. Like, why not finish this integration? So I'm going to actually talk through it, and then we'll see what they do. So what is the area? This is such a good one. Polar coordinates is such a good one. What is the area of this? Well, we're going to have a distance rho to this differential chunk. It's going to have a distance of d rho. You know what I mean? A little change in rho. That's going to be d rho. You could have delta rho, a little caret rho. You know what I mean? For that, however you want. And then as your caret rho reaches 0, you know what I mean, but however you want to do. But this would just be d rho in height. Now with this, you have as this gets real small, the top is still longer than the bottom, but it's, what do you call that? It's a trapezoid. So if you took the average between the top and bottom, I don't even want to do that. Yeah. If you took the average, because that's the other thing. I always forget to do this with differential areas. It's like you don't go a distance rho to this chunk and then add d rho. Is you put the chunk right in the middle, and then its differential width, or height in this direction is d rho, but it's centered right on this. So they have it drawn very correctly. I always mess it up. And I'm just wondering if other calculus books, because this is a differential element, I don't know. I think this is, but still, it's very useful to draw this distance to the center and then draw that d rho, on one side and the other. Cool. Because now we can figure out, now we know that the length of this top is longer, the length of the bottom is shorter, but the length in the middle is going to be the average length. So if we take, on a trapezoid, if you take that average, between them, which is adding top, adding bottom, dividing by 2, which is just the length of the midpoint of a trapezoid, that's your square. You're basically turning a square into a trapezoid. So we'll have d rho is the height, and then, so now what is this arc length? Well, we're going to have, and they should have done a little bit better job, but they don't, because they don't do the double integration. They don't say that we're going to double integrate d rho and then we'll have a d theta. So this is part of a slice. That's an angle of d theta. D theta is just an angle. We actually need an arc length. So we're going to take, I like to use the saying radians times radius is something normal. I say that first, and then I say radians times radius is arc length. And it's useful because radians per second times radius is tangential velocity. And angular acceleration, radians per second times radius is tangential acceleration. So this whole idea of radians times radius is something normal. I think is a very useful phrase. So hell yeah. So that's the way I remember it. And so I have radians is d theta, that's the angle, times the radius is rho. So I have d theta times rho is that length, the width of this square. So now I know the height of the square is d rho, and then the width, radians times radius, is d theta rho. So I have d theta rho times rho, or rho, the height of this is d rho, and then we have multiplied by d theta rho. So if we clean that up, we would have rho d theta. So rho d theta, and that's what that would be our two things to integrate. So if we said dA, so that's the area dA. The area dA, this little piece, is going to be rho d theta. So we pick up another rho, so we would have tau rho squared d rho d theta. And we would just integrate rho from 0 to r. That's easy. That just gives us an r. No, I'm sorry. Because we already have rho squared. So when we integrate, you have to account for that. D theta, we don't have, this won't have any other theta term. So we'll just have a 2 pi. So for this term, we'll just have 2 pi. But now we want to say but tau varies as you go along rho. So we definitely need that equation for tau to be rho divided by r times tau max. So we're going to put that in there. And so that gets us to where they did it. So we have this tau is tau max divided by r times rho. And they already put it with the other rho. And then what we're saying is dA is rho d theta. So this equation really should be, it can be. The derivative is T max divided by R, rho cubed d rho d theta. And then you're going to integrate the d theta. You pick up a 2 pi. And then you're going to integrate the rho cubed. That becomes 1 divided by 4. No, I'm sorry. No, it will. But you're going to go from 0 to r. You do have this r down here as a constant. T max is a constant. It's outside that integration. But rho cubed becomes, the integration of that is rho divided by 4 with limits from 0 to r. So you're going to get radius divided by 4 divided by 4. And then that radius divided by 4 cancels one of those. So you're going to get r to the 4th divided by 4. So your whole answer is going to be, and then you have a 2 pi. So you're going to have 2 pi r to the 4th divided by 4 times T max for a cylinder. And let's try to compare that. So we have 2 pi divided by 4. That's going to be pi r to the 3rd divided by, what the hell do we even say? We're going to have r to the 4 divided by 4, r to the 3 divided by 4, r to the 3 divided by 4, but times 2 pi. So we're going to have pi r to the 3rd divided by 2. So there you go. We're going to have r. And this is good. It's good for me to just do this by memory. It's probably sucky to listen to, but it's just like if you can also put it into, do things in your head is a very good skill. So we're going to have r to the 3rd times pi divided by 2. So we're going to have T max r to the 3rd. Or pi times T max r to the 3rd divided by 2. That's going to be the moment. And that moment is, that's going to be the total moment generated. And that total moment generated is equal to the torque. So the integration of this moment is T, big capital T. So when we integrate, we're going to have capital T, and we already did it. So we're gonna go back up and see what they did. But we should have, we should have this, and they don't even do it with just the radius, which totally sucks because now we're gonna have to. So you're gonna get this. We already got it. So actually, Here you go. So you're going to get, ooh. Yeah, and there isn't even an equation. So if this is t, we're going to get pi upstairs. So we got pi times t max, we already said that, times radius to the third divided by 4. So this is going to be pi t max d to the third divided by, divided by 2. We want to divide by 2. And so we're going to get pi times t max times d cubed divided by 16 is torque. You know what I mean? That's where it's just like these textbooks, they should show you at least like 4 different ways that say the same thing, because they just jump to, make too large of jumps. But we're going to see that if diameter is just r divided by 2, that's going to be r cubed divided by 8. So if this d is upstairs and it's going to turn into r cubed divided by 8, bummer. Oh, no, the diameter is 2 times, I'm sorry. Yeah, the diameter is 2 times the radius. So then the 8 cancels the 16 by a factor of 2 and puts a 2 downstairs. So hell yeah. So this is so wild that, the fact that right here they don't do the double integration, that would have helped. So torque, again, is this double integration, tau max r, rho to the third, times d rho d theta. Or rho squared, and then dA is that rho d theta. So you're going to have rho cubed. You're going to integrate that. That's going to go rho to the fourth divided by 4. Cool. And your limits are going to be from 0 to the radius. So that's going to be r to the fourth divided by 4. You're also taking r to the fourth divided by this r, so you get r to the third divided by 4. The integration of the d theta goes 2 pi radians. So you're going to get 2 pi divided by 4. That's going to be pi divided by 2. So you're going to get tau max r to the third divided by 2. So yeah, pi t max r to the third divided by 2. That's going to be torque. So if we have torque, so that's what we get right here. This says torque is equal to pi t max. D to the third is just 2 times the radius cubed, so that's going to be 8r to the cubed, or 8r cubed divided by 16. 8 divided by 16 is just divided by 2. So there you go. That is going to be your torque equation using that double integral. So now let's see what they did. You know what I mean? And this happens so much in textbooks that I guess I'm getting a little bit more used to it, but it happens all the time in this. Once you get to this rho squared dA, they just say, hey, the light bulb went on, because rho squared dA is the definition of polar moment of inertia, which does not change as long as someone made and manufactured this shaft. That value is just a function of its shape. It's not a function of what you do to it. So there you go. So this is, in a sense, this rho squared dA, it's an integral. And we have to, you know what I mean? But it is just a constant value. And worse, you can just look it up. And then so you're not even, people don't even do this. And you would still do this integral separately. You would still say, hey, I'm integrating. And if I was doing dA, it's still a double integral. I'm going from 0 to r. And then d theta goes from 0 radians to 2 pi radians. And you do that same thing. Integration of rho squared. And then this dA is just rho d theta. So I have integration of rho cubed. And I have that same thing. Just minus this constant. This constant wouldn't be there. But what they're going to say is that this term right here is just IP. And this is what I stands for moment of inertia, and P stands for the polar moment of inertia. It's the amount of material out from the radius, and all of it. Any material that's radially, a radial distance, counts, and that's what we get. And that's where if you just know the moment of inertia along like an x-axis or a y-axis, you would take that value, you would do the Pythagorean's theorem. You would take that value squared plus the y value squared, and don't quote me on, and the square root of that? Don't quote me on that. Yeah, polar moment of inertia is related to both the moment of inertia about the x-axis and y-axis. I think you just add them. I think whatever this one is, I don't know. Yeah, again, don't quote me. But if you know the x and the y, I think you just add them to get the polar moment. But hell no, do not quote me on that. And I shouldn't say things. It is all right though, because it makes you inquisitive. You're gonna look it up, because if you didn't, on stuff that we're unsure of, if you can't just be like, oh no, I'm hella % sure that what I just said was totally wrong, then you're unsure as well. And so that is, you're a % unsure. It's only by like association that you thought it was one way. And so it's good to relook those up just to refresh your memorization skills, but then also maybe dig in deeper of like, why don't I know that from intuitive perspective? I haven't done the equation or the math where I don't know, but anyway, so this value is going to be just that portion of the integral, and then this is a constant, and then so this value you just look up. So the torque is just going to be T max divided by R IP. And for a cylinder, this is the values for a cylinder, pi r to the 4th divided by 2. And we just did this one. I mean, couldn't we have done that one? IP for our cylinder is just rho squared dA. dA is that rho, d rho, d theta. And you already probably forgot about that. That's just the area of this little chunk. It has a height of d rho, done. But what's its width? Well, it's related to this angle, but I need to do radians times radius. So it's d theta times rho, or rho d theta. So I have d rho is a height, and then let's just do base first. So I have base is rho d theta, or d theta times rho. Radians times radius is that base or that arc length. So I have rho d theta times d theta, and I would rearrange that to be like that's rho d rho d theta, just for the integration. So that is one I would, but hell yeah. So again, just from verbiage, this dA is rho. We pick up another rho, and let's go down to this integration. So this integration is what we're doing. dA is rho d theta. So we have rho to the 3rd. And we're going to integrate that with respect to rho. That's going to be rho to the 4th divided by 4. And then integrate the d theta. D theta goes from 0 to 2 pi radians, so we pick up 2 pi. So we're going to have 2 pi r to the 4th, and then hopefully I didn't, So this rho squared, the rho cube goes to integration of rho to the 4th divided by 4. I'm going to say that one more time. But we have to, and the limits are from 0 to r. And then so that has r to the 4th divided by 4. So if this little piece is rho squared times rho d theta, we have rho to the 3rd d rho d theta. Integration of rho to the 3rd is rho to the 4th divided by 4. And then we're going to, the limits on that are from 0 to r. That's the radius of the cylinder, of a solid cylinder. And so we have r to the 4th divided by 4. Cool. And that's what we have right here, r to the 4th, at least that. And then integration of d theta is just theta. So when you integrate d theta, you get theta. And the limits on that are from 0 to 2 pi. So you have 2 pi. R to the 4th divided by 4. So 2 pi divided by 4 just becomes pi divided by 2. That's what we have, pi divided by 2 r to the 4th. If I say this radius is diameter divided by 2, I'm going to have diameter to the 4th, but I'm going to have 1/2 to the 4th. Well, 2 to the 4th is 2 times 2, which is 4. And then 2 times 2, which is 4, and then 4 times 4, which is 16. So I'm going to have a factor of 16 downstairs, so 2 times 16 is 32. and we have that value of pi d4 divided by 32. So yeah, so just for a cylinder, these are just given, and like I said, once it's manufactured, this polar moment of inertia, and that's where the light bulb goes on for a lot of these, is like if you ever get down to rho squared dA, you know what I mean, just, hey, let's just throw in this big old constant polar moment of inertia, because usually, and that's why it's so good to do tapered problems, because that means that your, well, I don't know. Yeah, it'll change, you know, along each slice. But for this one, each slice does not change. If you have two slices of this shape, that value just remains the same. Cool. So now we have our equation, and it should have been just right here. Torque is equal to T max R IP, and you can rearrange this for T max. That's R upstairs divided by IP times torque. So let's look at how they do that. So we have T max is T upstairs times R divided by IP. That's what we just said. T max upstairs times R divided by IP is T max. And again, that's all we were relating. We were relating to the stress inside the element and at the surface, because, you know, only if this number gets to be at the limit of the material, the yield of the material, then it's going to tear apart and do, you know, bend and break and kill people. Hell yeah. So that's the number that we can't go over. And then we want to know what torque, you know, and then we also want to do the problems in reverse. I just want to set up a system. I want to choose a chunk of steel that's cylindrical and solid off the wall, weld it to a wall, apply torque to it, and then just fathom or wonder what the shear stresses are inside. What sort of pressures are developing? And then this, I would just think of a number as well that is between 0 and some sort of max the material can take, which is usually the yield stress for design purposes. You don't want to get into like making your bar plastic, but I could weld that solid cylinder to the wall, torque on it, and know that it's going to get tweaked, and maybe feel that it didn't get bent. And then so I know it's within that limit. I just want to know what the value is. So if I want to know what the value is, I use this. I know what I torqued it, and then I'm going to take that torque times the radius divided by that polar moment of inertia, which you just look up. But that's the crazy thing, and I'm going to say this for these problems, is that the first problems you do, you should always go through this whole, I mean, if you're able to, because sometimes you're just not able to keep up with this. And then even for me, like I've tried to make 3 or 4 videos, like one a night on this topic, and I'm always just getting just a little bit tighter, you know what I mean? Of just like, oh no, that's the more important thing. And for this one, it was just like, well, wait a minute, like this value drives the integration equation. Like when we come down to here, this value for shear stress is what we need to know, and then we're going to know that stress acts on a little piece of area. That's going to be a force. That force is a distance rho away. That's going to be a torque, but that's just a little portion of torque. And then we have to sum all the torques about that circle. So I'm getting better at that, and I really do appreciate, you know, some of the bigs in the educational online fields, because they'll go the extra mile. You know what I mean? They're not just going to even call this a dA. They're going to say this is a caret A, a delta A. You know, some sort of area that we can actually envision, imagine, you know, but we know that we're going to have, it's not going to be the best, you know what I mean? Because like I said, if I take this outer ring as my, like, change in area, then, you know what I mean, the elements on the outside, 1, have a bigger stress, more pounds on them. 2, are farther away from the radius, they can take more torque compared to the elements, even just right there. If this is my slice, these elements, those little molecules, don't have the same poundage. There's less of them, and the distance is less. So all 3 of those things, all 3 of those stages accumulatively add up, and they are evident in the fact that when we're integrating rho cubed. You know what I mean? You know, and so that's an aspect of it. And so the farther things are away. So even our final equation is, even with this, because we have our polar moment of inertia, and you should always know that polar moment of inertia is a function to the fourth. It's whatever radius to the fourth, but our equation subtracts one of those radiuses. So honestly, so in this case, T max, our shear, is a function of r to the third, an inverse r to the third. I wish they wrote this equation for torque one more time. I don't even know why they didn't. That's crazy. Yeah, they don't even write it one more time. And that's what I definitely stress that. Like, this is an equation of 1, 2, 3, 4 terms. And this is actually blowing my mind right now. So you can put this equation in 4 different ways. Maybe I want to max out the material. So cool. Tau max is just going to be the max number for steel and shear. I know that. I know the material that's given. Cool. Well, if I know the material that's given, I know both of radius and IP. So that, so that's done. If I know, so then kind of if I know 2 things, I know everything. And so that's actually why this equation kind of sucks, because you should be writing it in terms, well, if you do know you have a solid cylinder, you use this. If you had a hollow cylinder, you would just integrate, but your radius, you have no r on the inside, so instead of 0 to r, you have your limits of integration are inner radius to outer radius, and that's going to pop up in this IP term. But yeah, it's just interesting how, if you have this formula, you can rearrange, and so I'm just going to say for this one, I can rearrange at least 2 different ways. I can solve for t as a function of everything else, and I can solve for T max as a function of everything else. So I think that is a good way to go about it. Hell yeah. But then this one, we got to do one more, because I would throw this IP term in here, and if we do, we're going to have, let's do that. So we're going to have pi downstairs. We're going to have r to the fourth downstairs. That's going to be r to the third downstairs once it cancels. And then we're going to have 2 upstairs. So we're going to have 2t divided by pi r to the third. Cool. And maybe I want to find torque. So if I have, what do I have? I have torque up top, and then downstairs I have 2, I have 2t divided by pi r to the third. So if I take this pi r to the third over here, I'm going to have t max. I'm going to have pi t max r to the third. And then divided by 2. So I'm going to have 1/2 t max, pi divided by 2 t max r to the third. So that would be my equation for torque. And then so if I should have my writing tools, I don't. And I don't really, I really enjoy this idea of just kind of talking through things and see if you can visualize and mentalize it. But we're going to have pi divided by 2 t max r to the third is equal to our torque. And then that's not even what I wanted to do, but in that case, if I knew my radius of my cylinder and I knew the max value I wanted, whether it was the yield, whether it was a factor of safety of the yield, then I could figure out how much I can torque that bar. But what I wanted to show is that right here we have an equation of 3 things. We have an equation of r, we have pi, we have pi r to the third divided by 2, or pi halves r to the third t max, or just as variables we have pi halves t max. I'm going to say that's a constant times r is equal to our torque. So let's get the r by itself. So I guess let me say this in words. So I have an equation that's a function of t max, torque, and r. I can rearrange this 3 different ways. And so you can see that if I put this IP down here, there's just another R. So I literally can either solve for T max, I can solve for torque, or I can solve for the radius. So maybe I want to know I'm dealing with a material that can take a certain max number in yield for shear stress. and I'm going to apply a certain amount of torque. So I know this is the material. So that's the other thing. This thing should generate a few things in your mind. One, it should generate the force, you know what I mean, on that material. It should also mean a force per area and a ratio that never changes for the material. So if you have a little chunk of material, it can only, take so much. Or if you have a number on that, it always means the same thing that you're doing. Whether that material stretches out or it's getting sheared the same angle between 0 and the max angle. And so that's where that this shear term should also jog that into your brain to be like, oh, this is the material that we're using, because you no, and then that's not 100% true. It's going to be the force over that area no matter what material you do choose. It's just that if you say that this is a material, materials will have a max shear stress. So that's a better way to say it. Hell yeah. So if we're dealing with steel, I know the max number that I'm wanting, the yield stress, let's say. And then I know that I actually want, so I'm using steel. That's all I'm saying. I'm using steel. I'm going to manufacture something. I'm using steel. I want to make a solid circular shaft, and I want to apply a torque on it of 100, pound-feet, sorry. But I want to apply a torque on it. And then the question is, well, what size do I need to make it? So then this equation you can rearrange for R. So I think that's going to be a very good take-home point, is like, hey, anytime that you see an equation with variables, ask yourself, what are the variables? Like you can rearrange, if this had 5 variables, you could rearrange the equation 5 different ways. And that's what happens with a lot of material mechanics equations. Even the fact that shear is force divided by area. Cool. So you're gonna have force divided by area. Torque. Anyway, so yeah, the number can add up, but it would be useful to write the equation 3 or 5 different ways to solve for all those variables independently, because then I could say, hey, the radius is going to be this upstairs divided by the tension. So that's going to be pi r to the 4th upstairs divided by 2t. You know what I mean? So there you go. Simple as... No. We need to solve for the radius. So I would have pi r... So I would have this part, when this goes upstairs, this part is upstairs, pi r to the 4th, t max. This part is downstairs divided by 2. So I'm going to divide it by 2t. And upstairs I'm going to have pi r to the 4th. I'm going to... Oh, yeah. See, we have to rearrange this like 100 different ways. Anyway, so I would get this pi r to the 4th up there. I would get this t max down there. And then I would get the pi down here. I would leave the pi down here. There you go. So if this IP is pi r to the 4th, I'm going to leave the pi downstairs. The 2 goes upstairs, so I'm going to have 2r. This r cancels. I'm going to have r to the 3rd. So I'm going to get this t max downstairs. So right now I have 2t divided by pi r to the 3rd. I'm going to get the r to the 3rd upstairs. And then I'm going to take the cubed root. So the radius is going to be the cubed root of 2t divided by pi t max. There you go. And so that equation should be written. You know what I mean? So, and I don't know. And it's cool to talk your way through things, because that's kind of the level that you would want to get on. So you're not just having to rely on paper all the time. So you can kind of see those things faster. Hell yeah. All right, so we are about done. But yeah, so let's see what other equations, you know what I mean? There's an equation for T max, function of tau, radius, and whatever the polar moment of inertia of your bar is. If we're using a cylindrical bar and there's your diameter, there you go. From this equation, we can easily see, hey, take the d cubed upstairs, take the T max downstairs, take the cubed root, and you can find that equation to solve for the diameter. Hell yeah. And again, this was the equation that we were using for that whole process, because maybe you don't want to know what the max is. Maybe you just want to know what's happening at any region. Let's see if that's what they're actually getting to. So yeah, you have this idea that the shear at any at radial distance is just the that radial distance divided by the actual radius of the cylinder times T max. So if we put this, and then so here's our equation as well. So instead of T max is equal to the tension times the radius, we have we want to know the stress at any distance. Well, and you can still see it's just a linear, that never changed. That's always linear. So this should be half of T max when rho is R divided by 2. So if rho is R divided by 2, we'll have T R IP divided by 2. And so let's go up here to what T max says. T max says TR divided by IP. So if we just divide this by 2, we have the shear at that rho divided by 2 distance. And so that's what this equation says. And so this was a video that just talked about this value of shear stress and had zero interest in figuring out what the angle of anything was. We briefly mentioned it, but we took it to the extreme. My cylinder shaft was 2 molecules in width, which I think is a very useful thing to do, because it gets you thinking of like, oh, that's still a cylinder. I'm still taking this disk of molecules and shearing them up against that disk of molecules. I have a torque applied to this face. If I take a cross-sectional cut between there, this face has to, and I take this chunk aside, that cross-sectional face has to balance. So if I have a torque on this face this way, the inside face will have an opposite torque. This opposite torque will be the equal and opposite on this cut face of this thing. So if I'm putting a torque on this portion and then I put that aside, hey, this inner part also sees that same torque, and that's the picture that we have right here. And sometimes that's the hardest part, is to be like, hey, I see this picture, but what slice, or where the hell is that even coming from? Cool. And this is the same longitudinal. So this is where you have to understand that, hey, for steel, your material's homogeneous. It doesn't really matter. It has an equal opportunity to rip apart in rings, or rip apart, in tension, or longitudinally. So just the fact that you have little squares that you're ripping apart, one down, one up. In that process, you could just think of it, don't think of it that way, take this little square, and you're actually ripping that square this way and that way. So those two things are happening. The only thing that's interesting with, that they definitely talk about with cylinders is, for the most part, if you tape, like this is just a rubber cylinder, and you tape a square or draw a square on it and you shear it, the diamond shape will be fairly vertical. So your square will turn into a vertical diamond. It's not going, because like if you just have these, if I drew the square here, hey, this face should go that way and this bottom face should go that way, and your diamond shape should look like that. But from experimentation, we don't see that. We see, most of the time the shape is just kind of in the up and down. It does not mean that is not getting sheared, because what happens is if you take an oblique diamond, that's perfectly, stretched along a 45, I can rotate it up along this y-plane, and then it looks like a diamond that's getting, stretched in the up and down direction. Or I could rotate it along the x-plane, and it looks like a diamond shape that's getting stretched one way and the other. But at no point is it not doing either of those? I mean, at all points, it's doing both those same things no matter which way you orient it. So this thing is equally trying to rip itself apart this way as it is this way. Even though when you draw it like this in a vertical diamond, it doesn't appear that these two faces are sliding past each other. But if you actually draw a horizontal line from them, you can see the distance they're sliding. And I think that deserves its own video. And I just apologize that I'm just not, I don't know. It's like, how could I make a little crispy 2-minute video on just that aspect? That you can either draw your diamond shape vertical, you can draw your diamond shape horizontal, or perfectly oblique. And at the same time, if you draw the perpendicular distances from one plane to the other, you can see that those planes are sliding across each other nonetheless. So hell yeah. Cool. All right, so that's it. And at no point, because we were saying at no point did I even get into the angle of twist. But we know, so I'll talk about this briefly. We know that, hey, if this is a max number, it's associated with a max angle. That's why I at least, talked about a ring of molecules, 100 molecules in a ring next to 100 molecules, and we're analyzing 4 of them in a square. One of the rings goes down, the other stays put, and we get a diamond shape to form. 2 of those molecules are getting stretched out, 2 are getting compressed, so we're talking about that. We're understanding what shear is. And we're understanding that an angle gets formed. So that diamond shape is the angle. That angle is indicative of how far those 2 diagonals are getting tensioned and how much these are getting compressed. That is what's holding the force. And that angle is a value. When it comes to steel, that angle is 0.004. So if I have this distance and this tiny angle that, this disc gets slid down, but imperceptibly. But if I add that disc next to another disc, next to another disc, and this angle is a 1 meter long, steel shaft, then that angle is still 0.04. But 0.04 times the radius, radians times radius, is 4 millimeters, which is the circumference distance that will get rotated. And I think for that first proof, I think it's way better if you think of how much this is rotating in circumference, because that value don't change. I mean, that value is a function of the stress on the surface that let's say it's max, this 0.04 angle. So it's a function of and then here it is the fact that we have this stress. The stress is related to the force on those 4 molecules, and the area between the 4 is just an area of 2. We've kind of talked about that. But Hooke's law says that, if you have this force to be max, the number is max, pounds per that area, then you get 0.004 radians. So you have, when this number is a huge value, let's say it's 36,000 psi, pounds per the area of inches squared, then you get a radians of 0.004. Cool. So those 2 things by Hooke's law are synonymous. And what we say is literally, 36,000 psi is equal to 0.004. But those numbers don't equal each other, so we need a proportional constant to multiply. And so if I took 0.004, I'm going to multiply by 11 million. And guess what I get? Let's say I get 44,000. So yeah, let's say this number is 44,000. Hell yeah. And so I'm going to take 0.004 times 11 million. I get 44 million. I get 44,000. 0.004 is 3 decimal places, and if I have 11 million, I go 1 is 1.1 million, 110,000, and then 1100. But times the 4 is going to be 44,000. Hell yeah. So anyway, so there you go. So these 2 numbers by Hooke's law, the stress is related to that angle. And when this number is maxed for the material, that angle is max, and that's always a good, useful place to start. Is like this angle could be an angle of 0.004. It's a small angle, But if this length is long, this shaft is long, like even just a meter long, that's 1,000 millimeters times 0.004 is the arc length of 4 millimeters. So this thing will rotate circumferentially by 4 millimeters. That doesn't give you angle yet, but you can just, angle is just a proportion of the entire circumference. So 180 degrees is just the circumference divided by, how do you say that? Like 180 degrees is the circumference divided by 2 times 360 degrees in a circle. You know what I mean? So there's a lot of ways. I think it's very useful to, do circles a lot of different ways. But anyway, so you're going to have 4 millimeters, whatever the circumference was, you're going to have that 4 millimeters divided by the circumference times 360 degrees. That'll give you the degrees of rotation. Cool. So then even there, if I know the length of this cylinder, I know the angle of twist, and then I can work backwards. If I twist a cylinder and it gives me a certain angle of twist, I can figure out what that circumferential distance is. I can know the length and that distance, know that this is a small angle, and find that angle. Let's say that angle is 0.003. I know the material is steel, and I'm a third of the, let's say the angle is 0.002. So I'm halfway to the max. I know that the shear stress, therefore, from Hooke's law, is going to be not 44,000 maxed out. It's going to be 22,000 psi, and sweet. And so that is going to be my max value. Maybe I want to know the max torque I can put on this, and then I just go back to the equation. So I go back to the equation. I know this is 22,000. I know my radius is whatever. I know the what cylinder I'm making it out of, and I can find the torque. And so there you go. So just from or is that wrong? So from that, what did we say? We said that if I have a cylinder and I do torque it, if I have a cylinder and I do torque it, I'm going to see an angle form. And if I measure that angle, I can find the circumferential distance it traveled. I can then go to the length and know the angle, and then relate that to the shear. And then once I know this, so I know this shear. I know this shear is 22,000. I know what my thing is made out of. I don't know the torque. So from that, I twist something, I look at the angle, and I want to know the torque. I twisted it, know the angle, I know the circumferential distance. So now we know that that's small angle, and radians times radius is that circumference distance. That is an equation that you would want to write 3 different ways because we want to solve for the angle. If I know that radians times radius is that circumferential distance, and I know this distance, then I would want to rearrange that equation. So radians times radius is C. I'm going to call that C for arc length, or S. So radians times radius is S. And I want to know radians. So radians is S divided by R. So whatever this distance is going to be divided by the length, and that's going to be, there you go. And small angle, that's just tangent. It's just opposite divided by adjacent. And it would be inverse tangent of that, but because it's small angle, you don't have to do the inverse tangent. Inverse tangent is just inverse sine divided by inverse anyway. So hell yeah, a lot of different ways to look at that. And yeah, what you would say is, this angle that forms is inverse tangent. So it's going to be arc length divided by length. And that's inverse tangent of that number is this. And the inverse tangent of that ratio is the angle. But you can say multiply both sides by tangent. So tangent of this angle is that ratio. But we can say tangent of the angle is sine of that angle divided by cosine, and by small angle, sine of the angle is just the angle itself, cosine of a small angle is 1, and we have angle divided by 1 is equal to this ratio, so there's another way to say it. So hell yeah. I don't know. I wonder if this is useful. Like doing no, because like the second I start writing things, it gets a little bit heady. But, mainly these videos are for like, hey, do you already know this? And you know what I mean? Am I ringing bells in your head that you can have an intuition for so you can just be way faster? Radians times radius is arc length. And what we did there is just like, well, maybe I want to know what the radians is. Well, that's going to be arc length divided by the radius. So arc length divided by r. And in this case, our arc length is maybe I just know the angle of twist. Well, that's the angle of twist divided by 360 times the circumference, and that'll give me the circumferential distance. But I swear even just that, if someone says the angle of 20 degrees and you want to know the circumferential distance that traveled, I don't know. I mean, are you just going to pop that out of your head that 20 divided by 360 is a proportion of that circumference? I mean, do you even think of angles that way? That 20 degrees is a proportion of a 360 degree triangle? And I think that's where working with proportions and also turning proportions into percentages. Like, what is 20% of a 360 degree triangle? Well, 36 degrees is 10%. And then, you know what I mean? Half of that, 18, is 5%. So 20% must be close to 5% of a circle. You know what I mean? So do stuff like that. It's very useful. All right, so hell yeah. So we are trying to do that first proof without looking at these stupid equations. I think they're not stupid. They show them first, and I think they overwhelm. And I think you really want to learn this proof from this shear perspective. No, I don't know. I just think shear is actually the harder thing to wrap my mind around. And it was the aha moment that is just like, hey, it's just a value. It symbolizes some force on some sort of area. And in this, like literally, it was not that complicated. We just needed an equation for shear as a function of the radius, which was just this. It was just knowing that we have a max at the surface, which don't change, given our thing don't change. And then it's just going to be rho divided by RT max. So this one equation, it doesn't have anything to do with twist rate or G or anything. And I was just so surprised by that. Like, it's like, damn it, that's the equation? You know what I mean? Like, that's the nuts and bolts. And so we talked about that. So that's tau. Tau is T max divided by, it's rho divided by R, T max. Hell yeah. And we integrated that. And so we did that. Tau is T max divided by R times rho, dA is that rho, d rho, d theta. Hell yeah. All right. So hell yeah. So we're talking about this in form of twisting. We twisted it. That gave us what this T max was. Should we do that again? We twisted this rod visibly. I see an angle form. I'm going to take that angle divided by 360. That's a proportion of the circumference. That's going to give me how much circumference this thing rotated. I'm going to say, hey, this is fixed to the wall welded, and now this line became this line. All those discs are doing the same thing homogeneously. We get a linear relationship. So therefore, if this circumferential distance is that, I use that radians times radius is arc length. I know the arc length. I know the radius. So I'm going to do radians times radius is arc length. I want to know radians, which is arc length divided by the radius. That's going to be this arc length that we took, which was the angle of twist divided by 360 times the circumference. And then I'm going to divide it by this length of the cylinder, and that's going to give me this shear angle. That's what's happening at the molecular level. We're getting one molecule of disks to slide across another molecule of disks, making an angle. That angle is hella small. But like I said, if you have a meter long bar, that small angle adds up to like 4 millimeters. But anyway, so we've already worked in reverse and we know what that angle is. Now we use Hooke's law, because any 4 little molecules of the same material, like steel, can only take an angle of like 0.004. So I'm going to compare that max number with the number that I just found, let's say it's 0.002, and then realize, that's going to be indicative of half of the max force on those four. And then we say, what is shear? Well, it's force on this side, and the faces. And so, but we don't have to even get that far. We can just know that the angle is associated with the shear. And then we said, what the hell is shear? Well, shear is force, on area, but we already did that integration. So we're already there. And so we know from Hooke's law, we found the angle, and now we just look to see from Hooke's law is just like, what's this shear? And so that's Hooke's law. Hooke's law says if this angle of those molecules is between 0 and 0.004 radians, that's its limit, and if it's halfway, it means it's going to be associated with half of this max, and not this max shear, but like the tau yield is the angle that those molecules, like that's the max angle they can withstand. For steel is 0.004. And so if I see that angle, that I know this value, and let's say it's 44,000 pounds per inch. If I see an angle of 0.002, just by linear relationship, you can do the equation on that one. I know this tau is going to be 22,000 pounds. Now, that's at the surface because that's what we're observing. I'm observing this angle, and I'm using this radius. At any point, I could have just said, well, let's not use the radius, and I want to know this. I want to know that this sweeps out an arc length. Well, at the halfway point, what's the arc length that it sweeps out? It's still the angle of twist times... and then divided by 360, that's the proportion of the circle. And then this little circle has a circumference, of pi r, 2 pi r. So you could do that. And that is useful because you don't just have to get this derivation from the exterior. And maybe this is even confusing where they should just draw this like at 3/4 of the way and stop, and just say that it continues, but we're wanting to find it at just a general location. So a lot of math and calculus books will do that, and then it's like if you know it at a general location, then you know it at all locations from 0 to r. So that's also a useful thing. Cool, it's T max, but I swear the fact that they just capitalizing this, just throwing this T max in your face and not saying that it has nothing to do with like the shear stress yield or tau yield or tau ultimate or tau allowed or tau designed. It's just all they're saying is just that's the location where you're going to see the max stress. That's where you're going to see this thing rip apart. And that's cool and useful, because then, I don't know, if it ripped apart on the interior and you couldn't see it, then you wouldn't know. So, but yeah, it's just by geometry, this thing rips apart on the exterior. Cool. So we did the angle of twist, circumference. We found that shear angle. Shear angle used a Hooke's law to find T max. And now we can go back to the equation to find the actual torque. And that was the whole problem. It's like someone torqued a shaft and we see that it moved an angle. Like think, hey, I want to know the circumferential distance it moved, because that distance, divided by this radians times radius is that arc length. So arc length is the kicker on this derivation, is that arc length relates, like that's the linking part, because this angle and this distance, this arc length right here is a similar triangle with there, which is your shear, which is a similar triangle to what you actually see for angle of twist if this is the full length of the rod. Hell yeah. And booyah. And so we did it. We found T max, and let's go to our equation, and we can throw that in for finding what T is. And if we rearrange this, or where's an equation for T? They don't even rearrange this equation for T. It's so dumb. Anyway, so if we rearrange this equation for T, I'm going to do T max times that polar moment divided by R, and I'll know what the torque is. So hell yeah. I don't know. So this was there were some moments in here that I have gotten a lot better on this derivation, but this was smart because In the last 3 or 4 videos, I just started from this perspective, you know what I mean, from this part, and I can get to about, I can get to about here, and then I just get winded. And so I just chose, I'm just like, no, I'm not going to do that. I'm going to start with Hooke's Law, linear elastic materials, and I didn't even actually say what G was. That can be for another video. You know what I mean? We just did it from an intuitive perspective. But G is just that number. Like I said, if I say that 44,000 is the force on the area in shear that steel can take, given 1 square inch of steel shearing it, and the angle that's going to form is 0.004. Cool. If this is 0.004 and this is 44,000, like what's this? It's 11 million. You know what I mean? So this value is just 11 million, and it has units to match. All you're doing is comparing 2 different things. It says this is apple pies and this is apples. Those are 2 different things. Whether you're going to the store to buy apple pies or buying apples, like one you're excited for, the other is just like, well, just stay healthy and stuff. But those are 2 different things. But if it takes 2 apples to make 1 pie, then 2 is equal to 1. But 2 as the number isn't equal to 1. So what number do we have to put right here? We have to put a half. But it kind of works, in reverse. I mean, yeah. So you have a really small number, 0.004 times 11 million is 44,000 pounds per square inch. Angle of 0.004 radians. So this number has to be 11 million pounds per square inch divided by radians. And because radians is dimensionless, this is just, 11 million pounds per square inch. Hell yeah. All right, I was pretty satisfied with this one. You know what I mean? We'll see. But hell yeah. I think this, for that student that was like, hey, can you do a video on shear and stuff? This is the one I wanted to do. And I just think if I did pen and paper, I just can't get as far. I'll get so exhausted. But I can go this far. I can do 2 hours, and it's really good for me to try to talk through some of those, I don't know, yeah. And this person actually might watch this whole video and maybe give me feedback. It's just like, man. But I just don't think people are going to watch a 2-hour video. But I still think I have something here. No one's doing this, just going over and just kind of like, hey, I'm kind of on an island, learning, and I want to learn more, and how do I do that? And you get to see the learning process. It's stumbly, but hell yeah, we get crispy. All right, thanks for joining me. Hell yeah.